Welcome. Today we're going to be talking about Laurent series. So Laurent series are definitely new territory. Before we've talked about Taylor series. And Taylor series, of course, we are, they're familiar from calculus. And so, it really is, we've just rehashed and used a lot of theory to prove that Taylor series work on the complex plane. And of course, we can write Taylor series like this. So if f is analytic, at z naught, then we can write our f is actually a power series, or essentially a linear combination of polynomials of the form an z minus z naught to the nth power, where an now can be written as f to the n over z naught all over n pi, or n factorial. And of course, this is precisely the Cauchy integral formula, which states that it's 1 over 2 pi I, the integral, at around some contour that encloses z naught of f of s over s minus z naught ds. Okay. Sorry. And that's to the n plus 1 power down there. Okay, so we keep seeing this Cauchy integral formula all over the place, and it turns out it's way more general than just finding derivatives. But it's worth just stopping for a second to go over what this is. Remember that f is analytic, which means that f is u plus iv. These are harmonic functions. We've already known that essentially averages of these functions around some disk will give you the point at the center of the disk, and that's essentially the proof of how the Cauchy integral theorem formula works. But it's worth to note that essentially what we're doing is we're trying to find information about f at a point f naught by sampling it on points nearby. So we have some contour c z0. We have z0 inside. I'm going to put z0 a little off center here. And basically what we have here is an average of f of s times some weighting, 1 over s minus z naught. And s minus z naught is, of course, that point right there. It's this distance there, s minus z naught is found there. And that's the weighting times ds over c naught. And then we just have to multiply by 1 over 2 pi I to get the factor to work out. And that's to the n plus 1 power, and that gets us all these derivatives at that point. Okay, and so we keep using this idea of averaging the function at a distance to get a value nearby, but we never actually have to evaluate the function at the point. We're taking an average of the function at points far away from z naught, and that allows us to not worry about if the function itself exists there or anything like that. But if it does exist there, of course we can equate it to derivatives. But it turns out it's even more general. This integral will exist even if the function is not analytic at the point z naught. All it has to do is the contour itself has to be in a domain of analyticity. So so that's just some rehash of things we've covered before. But now let's ask a basic question. The idea is that can I, so now we have this nice Taylor theorem, and this works for when f is analytic at z naught. But what about points z naught where f is not analytic? Can I find a series representation? And the answer is yes. Yes, indeed, you can. And again, before we get started on stating exactly how we do it or what form that takes, let's think about again. So when f is not, so if f is not analytic, right? You know, essentially, there's a if it's not analytic at a point at z naught, say, we know it's going to be something of the form. You know, a lot of times we find at least that there's a common form that z minus z naught to some power, we'll call it, k, right? And so this this division by 0 shows up. And it turns out, of course, we have a nice way of understanding those division by zeros. We can put them in like that. And it turns out that there is a nice way we can do it. So really what we're going to be exploiting is if I have some disk where it's analytic except for at a point z naught, right? What I do is I'm going to exploit the multiply connected domains. So I'm going to call D now. I'm going to actually, put a little disk that circles our point. And now in this domain right here, my function then is analytic. And then we'll use the Cauchy-Goursat theorem in order to establish, just like we did with Taylor series, where we found these coefficients by using the Cauchy integral formula. We're going to do a similar thing, but now on multiply connected domains, where we encircle our point of singularity, and we're able to find additional terms beyond what is in the Taylor series that can help represent our function. And the terms that we're going to find are going to look something like these sort of things. Okay, so that's just foreshadowing the proof. Now let's go through and actually directly do it. So again, we're going to start off just like before. We have some point z naught where our function is non-analytic. And we're going to draw a domain around that, and that's going to be formed by a contour we'll call C1, and it's going to have a radius capital R1. And then we're going to take another contour. I should have drawn a little bit bigger. I can do like that. We'll call a contour like that, another positively oriented contour. We'll call that C2, and that's going to have a radius R2. Okay, and now we're going to take a point Z, which is inside our domain. And in this domain, this is the domain of analyticity. Okay, so of course we can make sure that we think of that domain as being a little bit bigger than our contours, like that, so that the domain is, so the function is analytic even on the contours themselves. So that'll be our domain of analyticity. All right, and then what we're going to do is we have this z. I'm going to put another little contour around it. Okay, right. So it turns out, so again, I can represent Cauchy integral formula of a point z by taking average values around it. So we're going to do that for all three of these contours, and I'm going to call this contour gamma. All right, that's what they use in the book. So we have C1, which is small. And first of all, z is in between. So what we have here is the modulus of z. Now these are all annuli. So what we're going to have is this is going to be less than R2, right? And that's going to be greater than R1. Okay, so that's where our z will be located, and it can be any point inside of there. Okay, and so let's go through again. Now, remember from Cauchy-Goursat, Cauchy-Goursat said that if I have a multiply connected domain, I can actually express this integral on a contour, so the total contour, as a sum of individual contours. So what we'll do it is say that now the integral of C2 over C2 of f of s, s minus z, okay, is ds. So I'm going to take that, so I'm going to think of that as my integrand here, and provided s is out here, or sorry, z is out here, this function is we can but it doesn't work. We need to actually add additional terms to it now. Because this is positively oriented, I have to put a minus sign there, and now that's C1, and we have f of s, s minus z ds. Then we have a minus, another, because we can do what we always do, right, is to bring this inside, go like this, go around that contour, and come back out. Go around here, go into this contour, and then go around it. And we have to go around backwards now, and then come back out, and then continue along our path. That'll be gamma, but because we want gamma to represent the positive oriented contour, we have to put the negative signs there. Okay? So that'll be f of s, s minus z ds. Okay? So f is analytic there. And we should note then that, okay, so these two integrands for these two particular contours are not analytic. Not analytic inside C1 or C2. All right, but for this one, the integrand here is analytic. Okay, so actually we can rewrite this as just being the Cauchy integral formula, which states that this because this is analytic inside of there, that has to be equal to, oh sorry, the Cauchy-Goursat said that these things are all equal to 0. Sorry about that. This is the statement we have here. That's Cauchy-Goursat. As long as we have a multiply connected domain, and we have this point. So I should say that f of s is analytic on this domain, right? Not the whole integrand, but just f is analytic. And Cauchy-Goursat says that this multiply integration on the boundary of this multiply connected domain, because it's analytic in this region all through here, it should integrate to 0. Okay, so we've used all of our major theorems here so far. However, f of s is analytic on this domain, but f of s is not analytic within the domains enclosed by C1 and C2, because there's this point Z0 in the center where we're having problems, right? And so C2, of course, encloses that, and so does C2. But not gamma. Gamma is okay. Okay, so this then says that this has to be equal to 2 pi I f evaluated at z. Okay, that's what this thing equals here. So of course I can rewrite this and actually move this over to the other side, and then I get f of z is then equal to integral over C2 f of s, s minus z ds, minus integral C1 f of s, s minus z ds. Okay, all right, so one thing I'm going to do here is I'm going to change the sign of this by changing the sign of the denominator. So I'm going to go plus, and now I'm going to go z minus s here. All right. So now I have a way of representing f of z in terms of these two contour integrals together. Okay. And so first note that, again, the contour integral c1, that's going to be bounded, its radius is going to be below that of the modulus of z, the point that we're interested in evaluating our function at. Likewise, the contour here, c2, it has a radius that's bigger. Okay, so this, of course, the result here, this is going to look, this is going to be our Taylor-like series. I'm going to call it Taylor-like series. Is going to come out of this. And here we're going to have a different type of series. We're going to have something else. Okay, so that something else is going to be fairly, it'll be very interesting. Okay, so so we can do the same thing on this as normal. Okay, so in fact, I can um, I can I can just leave it at this. Even though that our function isn't differentiable there, we can write this just like we did before. And that's going to be the sum as n goes to n from 0 all the way to infinity of the integral c2 f of s over s minus z all to the n plus 1 power. This is just a rehash of the Taylor series that we've done before. So there's several steps in between here, but it's the same ones we've seen in the last video. And that's going to be all, oh, there has to be 1 over 2 pi I there. Sorry about that. Okay. And that is times z to the n power. Okay. And so this, of course, is that an coefficient. However, in this particular case, we're going to not equate it with derivatives. With derivatives fn evaluated at z naught, because because they don't exist. Not at that point. However, this integral exists just fine. It has this particular value, a to n, and we can compute this integral just fine. We can't equate it with derivatives. Okay, so we may not have a constructive way to compute this value, but certainly it does have a value there. And of course, these are the powers of z. So, but now the next question is, what can we do about this one? And so let's look at that something else and see if we can find out what it is. So I'm going to go to the next page. Okay, so that something else was going to be, again, what we had was f of z is equal to Taylor series, now plus integral over c1 of f of s all over s minus z dz, or sorry, ds. Oops, I made a mistake. It's going to be z minus s, okay, ds. There we go. All right. And now what we're going to do is do what we've done before. So before we use that sort of a geometric series type thing, but we're going to do the same thing. S minus, or be z minus s. We can actually write this as follows. It can be the sum of n equals 0 all the way to capital N minus 1 of s to the n all over now z. Now z is in the denominator of n minus 1, n plus 1. So notice here that z is in the denominator. And that's because what we're doing here is actually factoring out the z, right? We're taking z outside and doing one of these. So that's s over z, like that, okay? And of course, remember, let's go back to our contour. This is C1, and we had a C2 outside of there too, right? And our Z value is out here. So what we're saying is, and there's our Z naught, and so we have here an R1. What we're saying here is the modulus of Z now is actually bigger than R1, right? And that means that, and of course our S values are all along here. All the S values are there, and that of course implies then that the ratio of s over z, this is actually going to be less than 1. So that's how we want to take our geometric series approximation, right? And so that leads to this expression here. But now z is in the denominator. Okay, and that is the important thing going on here that makes it distinct from before. And then we have a plus, and then we have an s of capital N all over z minus s, and then we have a z again in the denominator right there. Okay, and so that's the big difference here, is now our z and powers of z are in the denominator. Okay, So just like before, we can pass the integral through these things. And so, but what we first want to do is just we want to let's do a little housekeeping here, and I'm going to do a shift, an n shift. So I'm going to take n and relabel it as n minus 1, and that just simply shifts my summation here. So that then becomes it becomes the sum going from n equals 1, right? Because I started at 0, and so now I have to start at 1 to create 0, right? So I have to put a 1 in there to create 0, and then it's still good. And instead of going to n capital N minus 1, now we're going to just capital N, and that just reorients things here. And then what I'm going to do is also, so just like before, now I have a z to the n down there, right? Because what we're doing is we're just shifting everything by 1 over. And now what we're going to do is, then we had before an s to the n in the numerator, but now I'm just going to rewrite things a little differently. I'm going to put it in the denominator as a negative exponent, and it's going to be negative n plus 1, because we had that shift there still. We still had that shift, okay? And that's just a little housekeeping. I know it's a bit complicated, but you can, if you sort it out, you can find out what it is. And then this other term here stays the same, z to the n over capital S to the n, all over z minus s. Okay. All right. So, all right. Now what we're going to do is we're going to, of course, multiply this by f of s, and then integrate over c1 ds. And same thing here, f of s, and that, of course, makes it equal to this top bit here. Okay, ds. We're going to pass it through this sum, this finite sum, and so, of course, now we have that 1 over z coming out. So we have that summation now coming out, n equals 1 to n. And now we have a 1 over z coming out front to the n power. And then we have inside here a c1 f of s to a s to the negative 1, s to the negative n plus 1 power, okay, ds. And that is now a coefficient so that's a coefficient that's attached to that sum. And then we're going to have this term here, which I'm just going to call sigma n of z, okay? Of z, right? And this is sort of this again is our error term. So it turns out now, what we can write down here, I'm going to rewrite this then, is we're going to rewrite this. I'm going to call that a set of bn's, okay? And now what we have here is, again, we can write this now as f of z is equal to a Taylor series, sum n equals 0 all the way to infinity of an, an z to the n plus, and now we have a new sum. And so this error term, of course, is capital N goes to infinity. We can prove that this, of course, that sigma n of z goes to 0. I'm going to leave that out. I think it's a very similar argument as what we've seen for Taylor series. We don't need to do another one of those. It'd be repetitive. I'd rather move on. And now we have a new component to our thing. So this is our Taylor series. And now we have a new one, a new bit here, which we'll call bn times 1 over z to the n, and n goes from 1 all the way to infinity, just like before. All right, and so now, of course, we have exponents in the denominator, and so we're going to more and more negative exponents, if you will, if you want to think of it that way. And now again, an is going to be equal to 1 over 2 pi I integral over c1, of c2 there, the bigger contour around here, of f of s of s minus z to the n plus 1 power ds. Likewise, we have bn is going to be equal to 1 over, I forgot my 1 over 2 pi there. Sorry about that. forgot that there as well. There should be a 1 over 2 pi. Okay, 1 over 2 pi I, integral over C1, which again encloses our singularity of f of s, all divided by s to the negative 1 plus n. So of course, as n gets bigger, this becomes, so if this is, and so we're going from n equals 1, right? So we start with no powers of s at all, but then this is actually going to, you could put this back in the numerator, right? So that, all right, so that's our result. So now we have a Taylor-like series, and then we have this new thing which we can call the Laurent terms. Okay. So the Laurent terms are here, and that has to do with powers of 1 over z, of course, which that is our singularities. So I'm just going to rewrite this statement now. Okay, so f of z. And so, of course, we can do a shift. Z goes to z minus z naught if we want. We can do such a shift, and we can get to the final result. So that's our shift. Okay, and that becomes then the series of the form n equals 0 all the way to infinity of an z minus z naught to the n power plus another set of terms n equals 1 to infinity of bn of 1 over z minus z naught to the n power there. Okay, so where an is going to be just like before, around some contour, and we can remove the labels on the contours. They just have to enclose z naught, really. F of s, s minus z, n plus 1 ds, and bn is equal to 1 over 2 pi I, integral over c, some contour that encloses z naught of f of s of s minus z to the negative n plus 1 power, okay, ds. Okay, so that's the main result here of this series now. So so that's our big result. So I should put z naughts in here now, right? So that can be our new. Sorry, I should just leave those alone. Those will just be z's. So now again, these are the Taylor-like terms, and this is the Laurent. Laurent terms. Okay, you can call them whatever you like, but there they are. But of course, these here represent the singularities. And of course, that z naught represents that point of non-analyticity. We have a division by 0 there, right there. Okay, so and now we have a constructive way of actually computing these things. But now, because we don't have derivatives that exist at this point, this thing can't be equated with derivatives of f, but is simply taken on face value that we have to do this contour integral. Okay, so that's the statement of the theorem. And again, what we do is we have some point of non-analyticity at z naught, and we coordinate off with a little contour. We find an annular domain, and we know it's analytic all through here. And so we're looking at points z that are away from that singularity, and we can find now a series representation at the point z of this series. All right, so thank you very much. And in a later video, we'll talk about some applications of how we can actually compute bn and an for specific values that are important for applied mathematics, and especially for signal processing. Thanks very much.